Are you ready for a planet that breaks the rules? Here's what nobody tells you about Uranus. It doesn't just spin, it rolls. And that one weird tilt changes almost everything you think you know about seasons, weather, rings, and moons. Imagine standing on a world where the sun can sit near the horizon and barely move. Not for a day, not for a month, but for decades. That's Uranus. It's an oddball, and that makes it one of the most interesting stories in our solar system. Let's get something straight up front. Uranus isn't just the blue one after Saturn. It's an ice giant with its own playbook. The planet is tipped over by about 97 degrees. To picture that, take a globe, lay it on its side, and spin it. That sideways spin is real, and because of that tilt, Uranus doesn't have normal seasons. Each pole gets about 42 years of daylight followed by 42 years of night. That's a child's entire life spent under one long sunrise that never really lifts, or one long twilight that never quite fades. Now, before we dive into the details, here's the simple version of the plot. Uranus is big, cold, and pale blue. It orbits far from the Sun, takes 84 Earth years to go around once, and spins in about 17 hours. It has rings, it has a bunch of moons, and it has a magnetic field that doesn't line up with its center the way you might expect. But the heart of the story is that tilt. With that one twist, the planet becomes a world of extremes, slow changes, and quiet chaos. So, what's the problem or challenge here? The challenge is that Uranus hides in plain sight. It looks calm, almost blank, when you point a telescope at it. For a long time, that fooled us. We assumed not much happens there. But the truth is, the planet is subtle, not simple. It holds on to its secrets. Its clouds are faint. Its storms are shy. Its rings are tight and dark. Its field is lopsided. Its moons carry clues that don't give up their answers easily. And we've only had one spacecraft, Voyager 2, flyby Uranus, and that was back in 1986. One quick pass, a handful of hours of close-up data, and then silence. That's the challenge. We're trying to explain a world with too few pictures and too many puzzles. Let's open the door and walk through the pieces, one by one, and make them easy to follow. Start with the color. Uranus looks blue-green because its air holds methane. Methane absorbs red light and lets blue and green slip through, so the planet's face has that cool, calm tint. But the air on Uranus is not like Earth's. The top part is mostly hydrogen and helium, the same basic stuff the Sun is made of, with a little methane mixed in. Deeper down, the pressure rises. The temperature drops, then rises again. Clouds form at different heights. The highest clouds are likely methane. Deeper layers may hold hydrogen sulfide and water, and far deeper there's an icy mix of water, ammonia, and methane crushed into a hot, dense fluid. It's not ice like the cubes in your drink. It's super-pressurized, weird-state ice, thick, heavy, and hot, even though the planet is cold at the top. That strange interior is why Uranus sits in a class we call ice giants, different from the gas giants Jupiter and Saturn. Now the spin. The planet turns once every 17 hours and a bit. That's a fast day for such a large world. But because the axis is tipped over, the spin is retrograde. In plain words, if you could hover above the Sun's North Pole and look down, most planets turn counterclockwise. Uranus turns the other way. That tilt plus the retrograde spin is a big hint that something hit Uranus long ago. Maybe it was a massive collision with an early protoplanet. Maybe it was a series of smaller hits. Either way, the result is the same. Uranus rolls around the Sun like a ball on its side. What does that do to the seasons? It stretches them. An Earth season is 3 months. A Uranus season is over 20 years. During solstice on Uranus, one pole faces the Sunday, the other pole faces away. The lit pole gets a sun that just circles the sky, never setting. The dark pole gets nothing but starlight, for over 4 decades. Then, as Uranus moves around its 84-year path, you reach equinox. At equinox, the planet's ring plane and equator align almost edge-on to the Sunday. Day and night split evenly, and the sun rises and sets like you expect. Then the tilt carries on, and the other pole goes into its long day. Think about that for a second. If you live near the pole on Uranus, morning and evening are more like life stages than times of day. You might think that long daylight means lots of warmth. Not really. Uranus is around 19 times farther from the Sun than Earth. That means sunlight there is weak. It's a faint glow, not a blast. And Uranus doesn't seem to give off much heat from inside either. Jupiter and Saturn glow with extra heat. Neptune does too. Uranus is different. It's quiet in the infrared. That suggests its inside is somehow sealed or layered in a way that traps heat differently. Maybe the tilt changed how the interior settled. Maybe the layers don't mix well. That trapped structure could be a reason the planet looks calmer and dimmer than its neighbors. Calm doesn't mean still. There are winds on Uranus that can run at high speeds. Some jets flow backward compared to others. There are storms that pop up, fade out, and hide under that soft blue haze. When Voyager 2 flew by, the planet looked almost featureless. Later, with better cameras from Earth and from orbiting telescopes, we saw bands and spots come and go. The patterns seem to change with the long seasons. When Uranus is near equinox, the day-night balance shifts, the energy input changes, and the planet wakes up a bit. When it's near solstice, that polar cap can look different than the equator. It's not the dramatic stripes and storms of Jupiter, but it's not a blank cue ball either. It's a slow rhythm that you only notice when you compare images across years. Let's talk about those rings. Yes, Uranus has rings. They're thin, dark, and easy to miss. Astronomers first found them in 1977 by watching a star pass behind the planet. As the star faded in and out, the dips in light gave the rings away. Today we count more than a dozen rings, with the brightest one called the epsilon ring. These rings are not broad and bright like Saturn's. They're narrow, made of dark material that doesn't reflect much light. The particles are mostly small, with a few larger chunks. Some tiny moons sit just inside or outside a ring and shepherd it, keeping the particles in a tight band by their gravity. Cordelia and Ophelia are two of those ring shepherds. The rings may be young in cosmic terms, or they may be fed and shaped over time by the moons. They could be made of dust and ice that's been darkened by radiation and micrometeorite hits, turning dull and charcoal-like. The ring system looks simple at first glance, but it has delicate structure, gaps, arcs, and changes in brightness that tell a story of constant small pushes and pulls. Now the moons. Uranus has 27 that we know of, and they have lovely names pulled from Shakespeare and Alexander Pope: Titania, Oberon, Ariel, Umbriel, Miranda, and many smaller ones like Puck, Portia, Juliet, Desdemona, Rosalind, Cressida, Bianca, and more. The 5 big ones, Miranda, Ariel, Umbriel, Titania, and Oberon, are the stars of the show. Each is different. Each gives you a clue about the planet's past. Miranda is the strangest. It's small, but its surface looks like it was smashed and glued back together. It has bright and dark patches, grooves, and what look like giant patchwork blocks called coronae. There's a cliff on Miranda called Verona Rupes that may be among the tallest known in the solar system, several kilometers high. Imagine standing at the edge and looking down into a shadow that seems to fall for miles. How did a small moon build such features? Maybe Miranda was torn apart by a big hit and then reassembled. Or maybe tides from Uranus heated its inside and reshaped it from within, pushing blocks of ice up and dropping other regions down. The lines and scars on Miranda tell of stress, heat, and movement, not silence. Ariel is brighter and shows signs of youth in places. It has valleys and canyons. It looks like ice flowed or faulted there, like something melted and refroze. Umbriel is darker, older, with more craters, holding onto the marks of time like a dusty attic. Titania and Oberon are larger, with big cracks and canyons that suggest they too were stressed and pulled, maybe by tides, maybe by the freeze and thaw of an icy interior. Some of these moons might have had subsurface layers of slushy water ammonia in the past. It's even possible that some small pockets could still exist. If so, that raises interesting questions about chemistry under the ice. We don't know yet. We need a closer look. And that brings us to the biggest gap in the story. We've only flown by once. Voyager 2 snapped our only close images, measured the magnetic field, sniffed the plasma, and moved on. We learned that the magnetic axis of Uranus is tipped by about 59 degrees from the spin axis, and the magnetic center is offset from the planet's center. That's odd. A tilted, off-center magnetic field changes how charged particles move. It can produce strange aurora patterns and uneven radiation belts. It might hint at the weird interior where the field could be generated in a shell of ionic water ammonia rather than a neat central core. On Earth, our field comes from a spinning iron core. On Uranus, it may come from a deep ocean of strange fluid, hot and under pressure, with charged particles flowing in complex ways. Let's pause and tie a few threads together. The tilt changes the sunlight pattern. The sunlight pattern changes the weather and the way the upper air behaves. The lack of strong internal heat seems to keep the planet quieter than Neptune. The interior layers might be arranged in a way that locks heat away, which also affects the magnetic field source. The rings are narrow and dark, shaped by small moons that are also shaped by the planet's gravity and the long seasons. And the big moons carry scars from heating and stretching that may connect to how the planet formed and how it tipped. Each part talks to the others. You might ask, what about the orbit? Is it odd too? The path of Uranus around the Sun is actually pretty normal. The orbit is a slightly stretched circle like most planets. What's unusual isn't the path, but the way Uranus travels along it sideways. Picture a rolling ball moving around a campfire. The orbit is fine. The attitude is the shock. Another good question is, why so cold? The top of Uranus is among the coldest in the solar system, with temperatures around -220 degrees Celsius in places. That's because it's far from the Sun and because the planet doesn't leak much internal heat. Jupiter and Saturn glow with leftover formation heat. Neptune gives off more heat than it gets from the Sunday. Uranus, not so much. There are ideas about why. One idea is that the ancient impact that tipped Uranus also stirred and rearranged its inside, creating layers that block heat from rising. Another idea is that its core cooled fast, or has a different mixture that doesn't move heat as easily. This isn't settled, but the lack of a strong internal glow helps explain the planet's softer look. Let's take a closer look at the winds and clouds. The winds on Uranus can reach hundreds of kilometers per hour, faster near the equator and poles, with a banded flow that reverses direction at different latitudes. The clouds ride along those winds. The high clouds are faint and often hard to see, but when the planet is near equinox, the contrast picks up, and we spot more features. Over time, we've seen bright storms burst into view and then fade. We've seen a polar cap grow and shrink. The air is thin and cold at the top, but it's still a living system that breathes energy in and out with the long seasons. Now the rings, a bit deeper. Each ring has its own orbit, thickness, and particle sizes. The epsilon ring is both the brightest and one of the narrowest. The fact that small moons can herd a ring is a neat bit of physics. When a small moon sits just inside or outside the ring, its gravity tugs on ring particles in a way that counteracts spreading. Without those shepherds, ring particles would bump and drift until the ring blurred out. The dark color likely comes from radiation and dust coating the ice over time, turning it gray or almost black. The rings tell you there's an ongoing balance. Micrometeorites grind particles, radiation bakes them, and moons keep the shape. What about the small inner moons? Think of them as stagehands, not stars. Moons like Cordelia, Ophelia, Bianca, Cressida, and the rest move in tight paths, shaped by the planet's gravity and by each other. They're irregular, cratered, and fragile. Their orbits can be crowded enough that small changes add up. Over very long times, some paths may shift. Every ring edge, every gap, is a sign of their quiet tug-of-war. The 5 big moons are where the stories live. We already visited Miranda, with its patchwork plates and towering cliffs. Ariel shows smoother plains crossed by long faults, hinting at ice that may have softened and flowed. Umbriel is darker, older, and crater-heavy, like a library of impacts left untouched. Titania has huge faults and canyons, as if it once stretched. Oberon shows big old craters and bright streaks, maybe from fresh ice thrown by impacts. Across these moons, we see signs that they were not just dead rocks. Something heated them tides from Uranus, decay of radioactive elements, past impacts, or some mix. On some, that heating could have driven water ammonia to move under the surface, then freeze and crack the shell. If pockets of liquid ever existed, chemistry could have brewed in the dark. That's not saying life was there. It's saying the kitchen had a few ingredients you'd want to test. Now let's deal with the elephant in the room. Why haven't we gone back? The simple answer is time and money. Uranus is far. Planetary missions take long planning and long cruises. But there's a strong push to return with an orbiter and a probe. An orbiter could spend years mapping the moons, sampling the magnetic field, watching the weather, and threading the rings. A probe could dive into the air and measure the gases, the winds, the temperature, and the tiny bits that make clouds. We want to know the exact mix of elements. We want to test how the field is generated. We want to watch a full season change up close. And we want to fly by the big moons at low altitude to search for signs of past or present internal heat. Why does that matter beyond curiosity? Because Uranus and Neptune are the class of planets we see a lot in other star systems. Many exoplanets are mini-Neptunes or sub-Neptunes with thick envelopes and icy layers. If we can understand Uranus in detail, we can read the language of those distant worlds better. We'll know what a tilted field does to a planet's atmosphere and radiation. We'll know how rings and moons evolve in low light. We'll learn how interiors layer and trap heat. That knowledge doesn't stop at our solar system's edge. It helps us compare thousands of other systems. Let's bring the tilt back one more time, because it shapes the climax of this story. Picture Uranus at solstice. One pole is in constant sunlight, the other in constant darkness. The rings are seen at an angle that spreads their shine across the pole. The pole soaks up what little energy it can. The atmosphere there becomes different from the rest of the planet. Hazy caps can form, winds may shift, chemistry can change with the light. Decades pass. Slowly the geometry changes. The sun starts to creep toward the equator. The rings look thinner from the sun's point of view. Day and night begin to balance. At equinox, the sun lights the equator head-on, and we see more storms and sharper bands. The planet, which people call bland, actually moves through very long-form weather beats. It's a slow dance, not a still life. And because we live on fast-spinning Earth with short seasons, we tend to miss that. We haven't watched long enough. Now, one more twist. That off-center tilted magnetic field doesn't just make strange auroras. It also means the space around Uranus, its magnetosphere, gets reshaped as the planet spins, and as it goes around the sundial. Charged particles get trapped in odd lobes. Field lines open and close in ways that depend on the angle of the day. If you were a spacecraft in orbit, you'd pass through regions where radiation spikes and dips, not just by position, but by time of day and season. That would make every orbit a lesson in moving targets. Let's imagine a future orbiter and what it would do. First, it would map the field over years to see how it breathes. Second, it would watch the rings through changing light, measuring particle sizes and the pull of shepherd moons. Third, it would fly by the big moons, scan their surfaces in high detail, and measure their gravity fields to look for hints of internal layers. Fourth, it would stare at the planet's clouds, tracking winds and temperatures across a full seasonal shift. Fifth, it would release a small probe to dive into the upper air and send back readings on methane, hydrogen, helium, and trace gases like hydrogen sulfide. Even a short plunge would change our models for good. While we wait for that mission, what can we say clearly about Uranus right now? We can say it's an ice giant with a sideways spin. Its 97-degree tilt gives it extreme seasons. It takes 84 years to go around the Sun and about 17 hours to spin once. Its air is mostly hydrogen and helium with methane that sets the color. It has thin, dark rings shaped by little shepherd moons. It has 27 known moons with the 5 big ones each telling a different story. Miranda, Ariel, Umbriel, Titania, and Oberon. Its magnetic field is tilted and off-center, likely born in a deep shell of weird, hot fluid. It gives off little internal heat compared to its neighbors. Its weather is subtle. Not dead winds blow fast. Storms pop up, and patterns shift with the seasons. And it's still, after all this time, underexplored. Let's make the most surprising fact simple. Uranus rolls around the Sun on its side. That's not normal, and it affects everything. Each pole spends about 42 years in light or in darkness. That's a lifetime of dawn or dusk. The planet looks calm, but hides fast winds and changeable cloud bands that show up more around equinox. The rings are real thin, dark, and narrow, with little moons working as shepherds to keep them tidy. The big moons are not just random rocks. They carry scars of heat and stress. Miranda's broken. Ariel is youthful in places. Umbriel is old and dark. Titania and Oberon are stretched and cracked. The magnetic field is weird tilted a lot, offset from the center, so the space weather around Uranus is not like Earth's, Jupiter's, or Saturn's. The inside may be layered in a way that locks heat in, which could explain the planet's quiet glow. Why does the tilt exist? The leading idea is a large ancient impact. That impact could also have created a disk of debris that later became rings and small moons. Or multiple hits slowly pushed the axis over and left behind leftovers that became the rings. The moon's orbits and the ring's structure are hints, like crumbs on a table after a meal. A future mission could sweep those crumbs into a clear recipe. What about life? This isn't a place for life as we know it on the surface or in the air. It's too cold, too thin, too harsh. The interesting thought is not life in the planet's air, but chemistry under the ice in the moons. If any of the big moons had a warm subsurface layer in the past, then water, ammonia, and simple organics could have mixed. With time and energy, interesting molecules could form. Again, that's not a claim of life. It's a reason to test. The payoff for even a hint of active chemistry on an icy moon is huge for science. Here's another angle people don't think about: navigation by seasons. If you launched a mission at the right time, you could arrive near an equinox or a solstice and plan your studies around it. Arrive near equinox, and you can see the rings edge on and the equator lit up, which is perfect for watching storms and the fine structure of the rings. Arrive near solstice, and you can study a bright polar cap and see how polar weather sets up under decades of steady light. Each arrival window tells a different story. If you care about naming and culture, Uranus is special too. The moons named after Shakespeare's characters give this system a personality that no other planet has. Titania and Oberon recall a fairy court. Miranda, Ariel, and Umbriel sound like spirits. If you're writing stories or making art, you can paint a whole mythos without leaving the real science. The planet is strange and elegant at the same time, with a hush over it that feels like a winter morning. Let's bring it all together with one more pass through the key beats. Uranus is an ice giant. Its air is hydrogen, helium, and methane, with methane giving the color. Deeper down, an icy mix of water, ammonia, and methane forms a hot, dense layer that acts like a global ocean under pressure. There may be a small rocky core at the very center. The planet's tilt is extreme, about 97 degrees, so it spins on its side and in the retrograde direction. That tilt likely came from a massive collision early in the solar system's history. Because of the tilt, seasons last decades. 42 years of polar day, 42 years of polar night, with balance at equinox every 42 years. The planet turns fast about 17 hours per day, but that fast spin doesn't lead to loud belts and storms like Jupiter's, in part because Uranus doesn't radiate much internal heat. Even so, winds can be fast, and cloud features come and go, especially around equinox. The rings are narrow and dark, shaped by small shepherd moons. The 27 known moons range from tiny irregulars to 5 majors, each with unique geology. The magnetic field is tilted and off-center, suggesting a complex internal dynamo in a shell of ionic fluid, not a neat central ion engine. We've only had one close visitor, Voyager 2 inches 1,986. We need an orbiter and a probe to turn mysteries into measurements. Here's the key moment, the reason this world should live rent-free in your head. Uranus teaches us that one dramatic twist in a planet's early life can echo for billions of years. Tip a planet on its side, and you rewrite its seasons, change its weather, warp its magnetosphere, reshape its rings, stress its moons, and maybe even lock heat inside its belly. It's a giant, rolling memo from the early solar system that says, small differences in history make huge differences in the present. So the next time you see a soft blue disk in a picture and think, quiet, Remember what's hidden in that calm, the longest dawns and dusks in the solar system, winds that race under a pale haze, rings kept in line by tiny shepherds, moons with scars that don't match their size, a magnetic field that refuses to point the way you expect, and a whole planet that rolls instead of spins. If you're curious, you've got great company. Scientists want to go back. Engineers are sketching orbiters, probes, and flybys that use gravity assists to make the trip. The timing matters, because arriving near equinox or solstice changes what you can see. But whether we arrive for a polar day or an edge-on ring season, the payoff is huge. We'll learn not just about Uranus, but about the most common kind of distant planet we're finding around other stars. Until then, we can still learn a lot from Earth. Better telescopes, sharper images, long-term watching across years, these build a time-lapse of slow weather. We can watch storms brighten and fade. We can measure the rings when they occult stars and see how dense they are. We can track the moon's orbits and test for tiny shifts. Each small piece is a step toward a clearer picture. And yet, even with all those careful steps, Uranus keeps a little distance. It's not dramatic on purpose. It's indifferent. It rolls slowly, keeps its secrets, and shows you only what you earn with time. Maybe that's the best lesson. Not all beauty is loud. Some beauty is a quiet planet turning sideways under a faraway sun, writing a story of long seasons, soft colors, and deep mysteries. Here's one last thought experiment. You're standing on Miranda near the edge of a massive cliff. The sky is a deep, dim, blue-green disk. The sun is a pale dot. Uranus fills a chunk of the sky. Its rings a thin line. You feel almost no wind, only the soft pull of low gravity. The cliff goes down and down into shadow. You look up and see the planet roll, not spin, and you realize you're watching an entire world with its own sense of time. Minutes mean nothing here. Seasons are decades. Generations pass between sunrise and sunset. That's Uranus. It moves to a rhythm our bodies don't know, but our minds can learn to hear. So when someone tells you Uranus is boring, smile. Tell them about the tilt. Tell them about 42-year days. Tell them about rings so dark they hide until a star gives them away. Tell them about a field that points the wrong way and a moon with a cliff that drops for miles. Tell them that quiet can be wild when you know where to listen. That's the story of Uranus, the ice giant that rolls. The world of long light and long dark. The calm face with a restless heart. It's the planet that proves one weird choice in the past can build a whole new kind of present.